Hi, in this video I'm going to talk about three items which are quite important but also quite simple to understand at the same time. The first item will be the following: representation of a signal for example x of t in terms of a superposition of shifted impulses. Now we know what we mean by an impulse function, shifted impulses. The second item is the concept of impulse response in linear time-invariant systems. Okay, we are going to see what we mean by this invariant systems. And finally, the evaluation of the response in LTI systems, that means linear time-invariant systems, by means of the impulse response. And that will be the convolution operation. So we are going to see these three concepts. Okay, now first of all, let us start with the first one. Now we know that an impulse is a rather peculiar signal which is equal to 0 everywhere except a single point, and for delta of t it is t equal to 0, where it is infinite in magnitude. However, the strength of the impulse is 1, meaning that the area is 1. The integral is equal to 1. Okay? Now, we also know the sampling property of the impulse. That means if we multiply an arbitrary signal by an impulse and integrate, we get the value of the signal at that particular time instant where the impulse strikes. Therefore, for any arbitrary signal x of t, we can write x of t as follows: the integral from minus infinity to plus infinity x of tau delta of t minus tau integrated with respect to tau. Now this is a very remarkable result because we are able to denote an arbitrary signal in terms of a certain operation, integration operation, involving shifted impulses. So you see, this is a shifted impulse. Okay? And what kind of operation is this? We multiply x of t minus tau by the term x of tau. So multiplication is one operation, and then we integrate. But integration is a a generalization of summation. Therefore, this is a superposition expression. That means we express x of t in terms of a superposition of shifted impulses. So the first item is quite clear from the properties of the impulse signal. Okay. Now, the second item is the concept of an impulse response in linear time-invariant systems. Now, first of all, what is a system? A system is a transformation which maps a certain input signal to an output signal. So this is our system. This is the input signal. X of t is the input signal and y of t is the output signal. So the system is just a transformation which transforms any input signal to a corresponding output signal. Now, in several applications, there are systems which are especially important, satisfying certain properties. Now, the first such property is linearity. Now, a system is said to be linear if the following condition is satisfied. If the following condition is satisfied, and that condition is if x1 of t gives us the output y1 of t, where x1 of t is completely arbitrary, and x2 of t gives us the output y2 of t, then any linear combination of x1 and x2, the input signals, will yield the same linear combination of y1 and y2. So c1 x1 of t plus c2 x2 of t will yield the output c1 y1 of t, okay, and c2 y2 of t. If x1 gives us y1, x2 gives us y2, then such a linear combination of x1 and x2 will yield the same linear combination of y1 and y2. Of course, x1 of t, x2 of t are completely arbitrary. c1 and c2 are also arbitrary constants or scalars. Now, the concept of linearity is, of course, a very important subject, and in fact, the underlying mathematical structure for the concept of linearity is the vector space. Okay, but here we are not going to go into the details of that setting, but rather give this quite straightforward definition of a linear system. The second important property satisfied by systems, certain systems, is time invariance. Now, time invariance is defined as follows. A system is said to be time invariant if the input-output pair x of t gives us y of t, okay, implies x of t minus t0 yields the output. Okay, let me write it here. If x of t minus t0 yields the output y of t minus t0 for any t0. Therefore, if the input x of t yields the output y of t, the shifted input will yield the same output but also shifted in time. So for linear and time-invariant systems, we have these two definitions or conditions satisfied. Now in linear time-invariant systems, the impulse signal applied as an input signal plays a very important role. The output obtained for an impulse signal at the input, for a unit impulse at the input, is called the impulse response. Okay, now we are going to use the impulse response concept to find the so-called convolution operation, which gives us the relationship between the input and the output in linear time-invariant systems. Okay, what about the definition of the impulse response? Well, in a linear time-invariant system, so this is our linear time-invariant system. In fact, it is abbreviated as LTI. So we have an LTI system, and the input of our system is x of t, and the output is y of t. Now, if x of t is equal to an impulse, unit impulse, delta of t, the output signal y of t is called the impulse response. And is denoted by h of t. So this is our LTI system now. And now, instead of a general input, we have delta of t as the input, and the corresponding output is h of t. Impulse response. Okay. Now the question is the following. Up to this point, everything is quite straightforward, but we ask the following question. Now, if h of t is given, now in other videos we are going to see the calculation of the impulse response for certain systems, for instance, covered by differential equations, etc. Suppose that h of t is given to us, and the question is, can we evaluate y of t, the output y of t, for any input signal x of t. You see, this is a very important question, and if we can answer this question, we are able to represent the input-output relationship in a linear time-invariant system. Now, the answer can be obtained quite easily as follows. Now, the first step is let x of t be an arbitrary input signal. So x of t is completely arbitrary. But remember, at the beginning of this video, we have seen that any arbitrary signal can be represented in terms of a superposition of shifted impulses as follows: x of tau delta of t minus tau integrated with respect to tau. You see, we have here a set of linear operations, namely multiplication of the shifted impulses by some weights and integrating. And integration is nothing but a generalized summation, as you all know. So, the second step is, now we know that delta of t at the input gives us the impulse response. So in our system, if the input signal is an impulse, the output is the impulse response. And at the same time, we know that delta of t minus tau will give us h of t minus tau. Why? Because our system is linear and time invariant by time invariance. The shifted impulse will give us the shifted impulse response. And if you multiply the shifted impulse by x of tau, as you see here, t is our variable and tau at the moment is fixed. X of tau, the output will be multiplication by the same constant times delta of t minus tau for fixed tau but variable t. And this is of course by linearity. And finally, the last step, if we add up these terms, that means we superpose them in the form of an integral from minus infinity to plus infinity x of tau, delta of t minus tau integrated with respect to tau will give us from minus infinity to plus infinity x of tau. Here of course this is h of t minus tau. X of tau delta of t minus tau gives us x of tau h of t minus tau. So x of tau h of t minus tau integrated with respect to tau. But you see that this is also by linearity. Why? Because integration is a superposition operation. It's a generalized form of summation, and therefore the condition of linearity applies in this case. So by linearity we have this result. But as you see, this term is nothing but x of t, the arbitrary input signal, Therefore, this term must be the corresponding output signal. Therefore, y of t is given in terms of such an operation: x of tau multiplied by h of t minus tau and integrated. This integral is called the convolution integral. Therefore, and it is also denoted by the following notation: x of t star h of t, the convolution of x of t with the impulse response h of t. So in linear time invariant systems, therefore, we are able to answer this question we have already asked in a very easy way. That means if h of t is given to us, then we are able to evaluate the output for any arbitrary input signal by following these steps. The idea behind all this derivation, which is very simple and straightforward, is the following. Any arbitrary input signal can be represented as a superposition of shifted impulses. Now, we know that our system is linear and time invariant. So the impulse will give us the impulse response. The shifted impulse will give us the shifted impulse response. The shifted impulse multiplied by a constant for fixed tau before integration, but variable t, will give us the same constant multiplying h of t minus tau by linearity. And finally, if we add up over tau by integration, we are going to obtain the output corresponding to any arbitrary input signal. The operation yielding the output is called the convolution integral and shown by the symbol x of t star h of t. So in this video we have answered or we have obtained expressions for three important concepts. First, the representation of an arbitrary signal in terms of shifted impulses, which is a very important operation in signal theory. And the concept of impulse response and how we use these concepts to answer the question related to the relationship between the input and output signals in a linear time invariant system. Thanks.